So like I said, the symbols that we've seen before are on the left. We're going to add 3 new ones today. Okay. I'll explain what they are. So these guys over here, brand new. Don't worry about them because we'll talk about them. These guys over here, you've seen before. These are the ones that you're going to continue to see and you've seen before. Okay. All right. So chapter 8 was all about confidence intervals. Confidence intervals. That's all chapter 8 was, right? Chapter 9 is something called hypothesis tests. Hypothesis tests. Okay. So, what are hypothesis tests and when do we use them? That's the first thing. Okay. So, confidence intervals are one of the 2 most common methods of statistical inference. Inference means to infer something, right? Not necessarily knowing for sure, but I have enough evidence to say this is true, right? Inference. Anytime you infer something, you don't know it for a fact, but you're pretty sure that knowing using the information that I have right now, I'm pretty sure this is the case, right? That's inference. Okay? So one of the 2 ways in statistics we have to do that. One is a confidence interval, we did that last chapter, and the other is a hypothesis test, which we're going to do this semester or this chapter. The second common method of inference is called a significance test. Hypothesis tests, significance tests, they're the same thing. Sometimes they're called hypothesis tests, sometimes they're called significance tests. You'll always have the word test in there, though. Okay? It allows us to weigh the evidence in favor of or against a particular claim, right? This is what we're going to do. Someone claims something. Someone says the true average GPA of students at Central High School is 3.2. That's a claim, right? What a hypothesis test does, or a significance test, is that claim true or false? But not really true or false. We say, is it false, or do we not have enough information to say it's false, right? We've kind of talked about this before. So when we look at a claim, we're either going to say, no, it's wrong, and here's why. Here's the evidence. Or we're going to say, you know what? I don't know if it's true. I just don't have enough evidence to say it's wrong. Okay? Kind of the guilty, not guilty thing that we've been talking about. So a significance test or hypothesis test is a formal procedure for using observed data, sample size, sample, to decide between 2 competing claims. These 2 claims are called hypotheses. There's 2 of them. A null hypothesis, that's the claim. Or the alternative hypothesis, which is based on the data, I think this is happening. Okay? Those are the 2 things we're testing. All right. The claims are usually statements about a parameter. We know a sample. I'm trying to make judgments based on the parameter. Okay? Like the population proportion or population mean. Okay? So hypothesis test. Here's a burning question for the day. Could this observed change be the result of chance variance? Or is the change so drastic, unlikely, that it is considered statistically significant? So let me give you an example. I just said, I make a claim. I said the true mean GPA for students at Central High School is 3.2. 3.2 GPA. Okay? That's my claim. You take a sample. You take a random sample of 20 students, 30 students, 40 students, 50 students, and their average was 2.8. Those aren't the same, right? Those aren't the same. One is a C plus and one is a B minus, right? They're close, but they're not the same. So what a hypothesis test says is what is the chances that if the claim is true, this sample happened, right? If my claim is true, so if I say my claim is true, If Mr. Flores' claim is true of 3.2, what are the chances that I could get a sample of 50 students and their average GPA would be a 2.8? Right? If that number is high, then I don't have enough information to reject my claim. So is Mr. Flores correct? I don't know, but I just don't have enough information to say it's high. If my probability is low, if I get a low one, then I can say, Mr. Flores, you're wrong. You're wrong. You can't, there's no way for the average GPA of students at Central High School to be 3.2. Not if I did my job correct and got a good sample. And it was 2.8. Okay? So these are off, but is it significantly off? Is it significantly off? That's what the question will answer. That's what hypothesis tests answer. How far are they off? Is it significant? Okay? Okay, that's essentially what we do for hypothesis tests. We're testing a claim. Okay, so the first thing is the hypotheses, the new thing, the new stuff is a hypothesis. We've never dealt with hypotheses before, right? You deal with hypotheses in science class, right? Biology, chemistry, those are stuff, psychology, you deal in hypotheses. We are going to start today. Okay, so the claim that we weigh evidence against in a significance test is called the null hypothesis. The null hypothesis. Okay, H sub 0. It looks like an O, but it's sub 0. H sub 0. Okay, the claim that we are trying to find evidence for is the alternative hypothesis, H sub A. Sometimes it's a capital A, sometimes it's a lowercase a, it doesn't matter. It doesn't matter, it's the same thing. It means alternative. Okay? So when we come up with our null hypothesis is these are going to be one of two things. Whatever the claim is, we say H sub 0. The claim is, if it's a proportion, we say P equals the claim, right? P sub 0 is just the claim. This guy, these are just claims. So whatever the claim is. Okay, so we're just reporting what the claim is. Today we're just going to do proportions. We'll do means later in the week. Okay? So H sub 0 colon, the true proportion is what? Or H sub 0 colon, the true mean is what? Okay, that's how we write the null hypothesis. Alternative. We have one of three options here. If it's a proportions, we have three options. If it's a means question, we have three options, right? So we say, no, the true proportion, so the true proportion is actually bigger than what I think is happening. The true proportion is smaller. I don't know if it's bigger or smaller, it's just different. Different, right? The true proportion, the claim is actually bigger than, or sorry, the true proportion is actually bigger than the claim. That's what these two mean. Okay? No, the true proportion is actually smaller than the claim. I don't know if it's bigger or smaller. It's just different than the claim. That's what those two mean. I don't know if it's bigger or smaller than the claim. It's just different than the claim. Okay? So if it's proportions we're dealing with, we're going to use one of these three guys. If it's means we're dealing with, we're going to use one of these three guys. Okay? And when we go through a test, I'll show you how to do this, but just mainly right now, just the symbols, right? So we use a lot of symbols here. Okay, understanding what the symbols mean. All right. Okay, so here are our steps for hypothesis tests. We had 5 steps for a confidence interval. We're going to add 2 more steps. Okay? The two steps that we're going to add that we've never dealt with before are right here, number 2 and number 3. These are the new steps that we're going to add. Everything else you've done. It's a new formula we're going to use today, but we've done that before, right? So these are the new steps. We have to give our hypothesis statements. What is the null? What is the alternative? And then we have to state what's called the significance level. Significance level. Okay, and we'll talk about what a significance level means right now. Okay, so number 1, step 1, identify either the true proportion, true mean, right? You've done that before. You've did that on the test. You've done that on quizzes. You've done that on homeworks. That number 1's not any different. 2 and 3 are new. 4, we have to give the formula that we're going to be using. And I'll give you the formula. It's in here. I'll show you the formula in a second. Conditions and assumptions. It's the same. The same as you've been doing for 2 chapters now, since chapter 7. I'm not adding any conditions or assumptions because our data comes from a sample, we have to do those. Okay? Calculations. Calculations will look a little differently because, well, I won't get into it right now, and then conclusion, right? Okay, so what is a significance level? We talked about a hypothesis. What is a significance level? A significance level is kind of the bar that we need to meet. Okay? Usually it's 5%, 0.05. But sometimes it's 10%, sometimes it's 1%. Okay? For tests that require a higher level of confidence, we use a lower alpha level. Let me read that one more time because it's kind of opposite of what you think. For tests that require a higher level of evidence, more evidence to prove a claim wrong, we actually use a lower alpha level. That's a multiple choice question waiting to happen right there. What happens if we want more evidence to prove they're wrong? What if we need more evidence to say that person's guilty? I don't want to just be like, they probably did it. I want to be pretty sure. I want to be pretty darn sure that this person is guilty. That's raising the bar, right? Well, actually, when you raise the bar, you actually lower alpha, right? So 1% alpha means I need a lot of evidence. I need a lot of evidence to say they did it. They're guilty, right? If I don't have that evidence, all of that evidence, I have to say not guilty, right? 5% is usually the default, right? What was our default confidence interval? Which one did you see a lot? What percent confidence interval did you see like a lot? More so than others? 95. 95 you saw a lot. Guess what? We're going to see an alpha level of 5% a lot because 95 plus 5 makes 100. Okay? So a 1% goes with a 99% confidence. 99% confidence, right? What happened when we wanted to be very confident, right? Our interval got wider because I need more leeway. You want me to be really confident, right? 10% is usually the highest alpha level, the lowest amount of evidence needed. 10% goes with a 90% confidence interval. Okay? So most of the time, 5% is what we're going to have. But sometimes they don't say in the question. So if they don't say, our default is 5%. Okay? Okay, so here we go. Is our result statistically significant? Okay, my sample is this. The claim is this. They're different. Are they statistically different? That's what a p-value answers. We're going to talk about what a p-value is in a second. You've actually done p-values since chapter 2. You just didn't know they were called p-values. So calculating p-values is the calculations. And when we do it, you're going to be like, I've done this before. Because you have. Okay? So based on our p-value, probability value, right? We either reject the claim. Nope, Mr. Flores, you are wrong. It's not 3.2. The true GPA is not 3.2. That's rejecting a claim. I reject that claim. Or if our p-value is too high, greater than alpha, we say, Mr. Flores, I don't know if you're right or wrong. I just don't have enough information to say you're wrong. That's failing to reject. Okay? We never say you're right. Mr. Flores, you're right. 3.2, that was right. No, we never say you're right. We never, ever, ever accept the answer. We always, always, always just either say, we reject your claim because p-value was really small, or fail to reject because our p-value was too high. Okay? Conclusion on the back. Since we compare, so the three things we need to do are compare p-value with alpha, state whether we reject or fail to reject the null hypothesis. That's the second thing. And the third thing is, do we have enough evidence to say you were wrong, or do we not? Right? So if we reject, I'm going to color code this to make it easy. If we reject, we have enough evidence. If we fail to reject, we always lack evidence. Reject means you're wrong. If I call you a liar, I have to have evidence, enough evidence. If I fail to reject, that's like saying, you know what? I have some evidence, but it's not enough to call you a liar. So then we means we lack evidence. Okay, so reject and have go together. Fail to reject and lack go together. Okay. Interpreting p-value, you can read that. I'm going to get to what p-value is. Here's p-value. P-value of a test is the probability of getting evidence for the alternative hypothesis as strong or stronger than the observed evidence when the null hypothesis is true. Okay, so what that means is this. I gave you my example, right? I said the true mean GPA of students at Central High School is 3.2. That was my claim. I got a sample of 50, right? And out of that sample, it was 2.8. What my p-value will say is, what is the probability that if your claim is true, what is the probability or what is the p-value that I got a sample like I did? Okay, one more time. So what a p-value says is, if your claim is true, what is the probability that I got a sample with this average? Okay, that's what a p-value is. If what you're saying is true, what's the probability of what happened, right? If you're saying something is true and there's a low chance that this happened, that's a low p-value, right? It means you have to be wrong, right? If there's only a 1% chance of this happening, given this is true, then that's the 1% chance of happening. If I said there's a 1% chance of raining today, and it rained, I had to have been wrong, right? Because 1%, if it's like 50-50, you're like, okay, it might rain, it might not. If it rains, I wouldn't be shocked. If it doesn't rain, I wouldn't be shocked, right? But if I said there's a 1% chance of raining today, and it rains, that'd be pretty shocking, right? Because it's pretty low. 1% is really low, right? It's the same thing. It's the same thing. Okay, this will make more sense when we start doing an actual test, It'll make more sense because we'll be able to put it in context. Assumptions, same. Only for proportions, though. This is only for proportions. Don't try to use these for means. This is the same ones you've been using since chapter 7 for proportions. Okay? Don't mix up means and proportions. Okay? All right. All right. So now let's look at one. Let's look at a problem. Let's go through every for this problem. Okay? We're going to go through all 7 steps. Okay, so the mutating disease problem, 1A. It is believed that the vaccine for a horrible disease has been effective on 62% of its recipients. Okay? Medical research teams have been tracking this horrible disease and are looking for evidence to see if perhaps the vaccine is now less effective than it used to be. That would be because maybe the disease has evolved. Happens all the time, right? Even before COVID. Flu. We had flu shots. People get flu shots. Flu shots are vaccines, right? What's the purpose of a vaccine?
To prevent you from getting it.
Not necessarily. It could do that.
If you catch it, it prevents the symptoms.
Exactly, right? So a vaccine could do one of 2 things. It lessens the chances that you'll get the disease. And if you do get the disease, you won't get as sick, right? That's what all vaccines do. COVID, flu, there's other vaccines too out there. That's what vaccines do, right? So what they're saying is this horrible disease has a vaccine. So in the past, it's been effective 62% of the time. That means 62% of everyone who's taken the vaccine, either they don't get the disease at all, or they don't get as sick as everyone else, right? That's what that means. So for it to be effective, that's what it means, right? So 62%. That means the other 38% got it and got really sick. Okay. So now what they want to see is, has that disease evolved? That's what happens every year with the flu vaccine. Flu vaccine's gone, it's been decades since the flu vaccine's been available. What happens is every winter, every cold and flu season, the flu changes a little bit. The flu changes, the strain changes a little bit. So they can't give the same vaccine every single time. They tweak it a little bit, right? They tweak it a little bit. Well, that's what they're checking for here. They're saying, has it evolved? Do we need to tweak our vaccine so that we can keep that 62% or go even higher? Okay, because 62% is kind of low. Okay. So the vaccine is administered to a random sample of 450 adults, right? And after following these subjects for a period of 3 months, was found to be effective on 259 of them. So 259 of them either didn't get sick within that 3 months, or if they got sick, it wasn't that bad, right? It wasn't as bad. So the question is, does this provide evidence that the vaccine has become less effective? There's a lot to unpack there. Okay. Does the question anywhere say anything about a hypothesis test or a significance test or a confidence interval? Does there words anything like that in the question or prompt or anything? No, right? How do we know if we need to do a test or a confidence interval? Well, last chapter, the questions always said, no, not that one. Use a constructed confidence interval, right? If they want you to do a confidence interval, they'll tell you, do a confidence interval. If they want you to do a test, they might not always tell you, do a test, but there'll always be some keywords, and I'll highlight them. You'll always see the words, provide evidence. Provide evidence. That's key for do a test. Do a test. Okay? So sometimes they won't say, do a test, but they'll put little buzzwords in there, phrases, provide evidence, right? That means test. Okay? So they want us to do a test to see if the vaccine has become less effective. Okay? So we're going to use our sample. What's our sample size on this one? Before we get started, let's note what's our sample size? 450, good. Now, is this a proportions or is it a means question? Proportions, right? This out of 450, right? So we're going to say p hat equals 259 it was effective on. It was effective on 259 of the 450 people. Okay? So in other words, let's crunch some numbers. A little over 57%, 0.576, right? It was effective. Okay. Okay, so the first step, population parameter. I started it out for you. P equals the true proportion of, this is where they don't really give you, like confidence intervals, they always said the true proportion of, it was kind of given already, right? Here they don't do that as much. So we have to kind of figure it out on our own. So we do know P hat though, right? P hat is 259 out of 450. What does that proportion represent? The true proportion, not the true, sorry, the sample proportion of people that were where the vaccine was effective, right? Well, expand that for P. The true proportion of people for which the vaccine was effective. Do we have that number? 62%. For the past, I do. Yeah, for the past, I do. It's 62%. We want to see if the new number is bigger, smaller, different than that. Okay, so we do have 62%. Hypothesis. Hypothesis. So first thing we do is our null hypothesis, H sub 0. It's proportion, so we're going to use a P. What is the claim about the effectiveness? So that's what we're going to do on our alternative. Our alternative will be greater than, less than, not equal to. What is the claim, though? The going claim that what is the true proportion for which it's effective? 62. It's 62. True, the null is always equal to. The alternative is the one where it's greater than, less than, not equal to. Which one of the three options from earlier is this one going to be? Why less than?
Because they're trying to figure out if the vaccine is less effective now than before.
That's what it said in the question, right? That's what we're testing. We're testing what it says in the question. And the question says, is it less effective? I don't care if it's more effective. I just want to know if it's less effective. That's to answer the question. So we want to say, we're going to say less than. We want to know if it's less than what they have claimed in the past. Because if it's less than, that means it's less effective. That means it's evolved. Okay. Significance level. They don't say a significance level. Nowhere in there does it say anything about significance or alpha or anything like that. So we're just going to use 5%. That's our default. 5%. Okay.
When we do our significance level, will they specifically state this?
Sometimes they will. Sometimes they will. Sometimes they won't. Okay.
How can a number be different but not smaller or bigger?
So it could be. It could be bigger. It could be smaller, right? So for this, why did we choose less than? So the number could be bigger. The true proportion could be bigger than 0.62, right? Or it could be smaller than 0.62. Or it could just be different. The reason we chose less than is because to answer our question, which is right here, right? All we care about is if it has become less. So that's what we're testing.
But like in general, how can a number be different but not lower or above?
It could. It could be. Oh, okay. I see what you're saying. When is it going to be different, not lower than above? I actually have a problem here. If you look at the last page, there's an example there. It'll say, is there convincing evidence that the proportion of household differs from the claim? So when they don't use a word like less than or greater than, then that's when we use the not equal to. It'll always be in the question as to which one of those that we use. Yeah. Okay. All right. Assumptions, conditions. This is the same thing we've been doing for the last 2 chapters. Now the 3rd chapter we're doing this. Conditions. Check. Everything, our calculations are going to be based on the sample of 450. Because it's based on the sample, we have to do assumptions and conditions. Okay?
Do we still use the like SRS 10% condition?
So here are the ones we need to check right here. First one, sample. Is it a random sample? Were the 450 people a random sample? So the 450 people, it actually says a random sample of 450 people. So yeah, stated. %% condition. Little n is less than or equal to 10% of big N. Okay. We know what little n is, 450. We don't have a number for big N, right? We don't have a number. But in words, who would be big N? Yes, there you go. All people who took the vaccine. Because 450 are a random sample of 450 people who took the vaccine, right? So if that's little n, big N would just be all of the people. Who took vaccine. Okay. So for that to work, the number would have to be bigger than 4,500. If it's a horrible disease, you pretty sure that the number is going to be bigger than that. I mean, you know, look at the percentage of people that have taken the vaccine for COVID. You're talking millions, right? So, and that's COVID. From what I'm reading, this is a horrible disease. So the more horrible, the more chances that people are going to take the vaccine. Okay. The calculator?
I have your 6 too.
Oh, perfect.
Okay.
Yeah, take what you need.
Okay, thank you.
Uh-huh. Oops. Yeah, no problem. Last one, is shape approximately normal? Okay. We're not going to use central limit theorem for this guy, remember? Because central limit theorem is only for means. This is not a means. This is a proportions. So what do we use? Same one we've used in the past, n times p. I hate how they use q. Q is the same thing as 1 minus p.
So when we write it, will we be taught that points if we don't put the Q?
No. Okay. Q is, so if you see Q, it's just 1 minus p. It's the same ones we've been using for the last 3 chapters now. Okay. So n times p is greater than or equal to 10. And n times 1 minus p is greater than or equal to 10. Well, n is 450. N is 450. What is p? Give you a hint. We've already written it down. No, that's p hat. You're close. What's p? We actually know p. Yep. It's part of our hypothesis, right? That's the claim. P is the claim. Okay, pretty sure since our sample size is fairly big enough, pretty sure both of them are going to be okay. That one works. Oops. Not 0.62, 1 minus 0.62, which is 0.38. 171. Yep. So both are big enough. So especially on tests and quizzes, when you're doing conditions, I find that every chapter, when I'm grading them, conditions assumptions kind of shrink, right? Every chapter, when I'm grading them, don't let them shrink. They're just as important as everything else. Okay? So these are just as important. The nice thing about this is they're always the same. Chapter 7, chapter 8, chapter 9, chapter 10, they're all going to be the same. I'm never going to say, oh yeah, guys, we have a new condition we need to check. That's never going to happen. It's always the same. Okay? All right, so test statistic formula. For proportions, this is the formula. It looks crazy, but it's not that bad. First of all, what does it look like? What does it appear to be? What kind of formula does it appear to be? Right here, right? This is standard deviation. Don't you have that formula? You have that formula on your formula sheet, which you can use on tests, right? And then on top, what are we doing on top? Subtracting. And on bottom is standard deviation. What is that? Z-scores. That's what I was going to say. It's a Z-score formula, right? It's just a Z-score formula. It looks more complicated than that because it's got P's and P zeros and P hats and all this other stuff. But that's all it is.
Is this also one of the formulas that's on our formula sheet?
This part right here is on your formula sheet. That's the hard part, right? The hard part is memorizing that part. You don't have to. It's on your formula sheet. It's on your formula sheet, I think, twice. Let's see, where's your formula sheet? There we go. Nope, that's not it. It's part of chapter 7, right? It's right there on the front. And on the back, it's right here. Okay, it's the same thing. All right. Okay. You don't have to have the P zeros. I just cut and pasted it from a textbook that uses P sub zeros. You can use just regular P. So you don't have to have the P sub zeros. Regular P is okay. P sub zero is always the same as P, the claim. P hat is P hat, the sample. Okay. Okay, so calculations now. We're going to use that. So since we have a z-score formula, we're going to find a z-score. So the first thing we got to do, we've been doing this since chapter 2, is draw a curve, normal curve. That's the first step we've always done, right? So we draw the curve. Put the mean. What's the center? The claim. Claim is always going to be in the middle. Good. The claim always goes in the middle. What was our hypothesis? Or sorry, our alternative? Which is less, right? And then which way did we say, which symbol did we use? Less than, greater than, not equal to? Less than, right? So which way is less, left or right? Left. So we're going to shade that. That's going to be our p-value. Whatever proportion or whatever probability is in that green is our p-value. You've been calculating this since chapter 2. We just didn't call it a p-value. We called it a probability or a proportion or, but now it has a name. It's called the p-value. Okay. All right. So let's use our formula. Z equals p hat minus the claim. P hat is 0.576 minus our claim, which is 0.62. P sub 0 is the claim, so 0.62 times 1 minus 0.62 divided by the sample size, which is 450. And that'll give us our z-score. Okay. So let's crunch some numbers. Let's see. It's going to be negative. Yeah. Let me see here. Where am I at? Here we go. 0.576 minus 0.62 divided by, I got negative 1.92. That's what I got too. That's the z-score for this guy. What's the z-score for the mean, 0.62? What's the mean? What's the z-score? What's the z-score for the mean always going to be? 0, right? Okay. Are we going to go to our z-score tables, or are we going to use our t-score tables? Which one do we use? We got 3 tables to use. 2 on the front, 1 on the back. Z-score because it's proportions, right? Z-score so because it's proportions. So we get 0.0274, yeah. That's our p-value. I should have labeled this. P-value equals. Okay. That's our calculations. Our calculations are only to find the p-value. We just did that. Last step, last thing. Conclusion. Conclusion. Conclusion needs 3 things. First thing, I need to compare what p-value did I get versus the significance level that I set at the beginning. Is it bigger? Is it smaller? Compare the two. That's the first thing I need to do. Based on that, I either have to reject or fail to reject. Never, ever, ever accept. And then we put therefore, we either have or we lack significant evidence to suggest that. Okay, so let's do the first thing. P-value. Since p-value our p-value was 0.0274. What was our alpha level? What was our significance level?
0.05.
Okay. So is it bigger or smaller than that? Smaller. So we're going to say less than alpha level, which is 0.05. Okay. So we have two options. Are we going to reject or are we going to fail to reject? How do we know if we reject or if we fail to reject? Right here. If p-value is less than alpha, we reject. If p-value is bigger than alpha, we fail to reject, right? All of the pink ones go together, all of the green ones go together. Okay? So depending on whether our p-value, if our p-value is too big, it's going to be bigger than, means we fail to reject, we lack evidence. If our p-value is less than, we reject and we have enough evidence. So ours was less than, right? Ours was less than. So that means we're going to reject the null hypothesis. Okay. We reject the null hypothesis okay. Since we reject, we have significant evidence. I usually do two sentences. I mix the first number one and number two in the first sentence, and then number three, I do its own sentence. Therefore, we have significant or sufficient or enough evidence to show or to suggest that H sub A in context. H sub A is the alternative hypothesis, right? Alternative hypothesis is right here. We have to put that in words. Last thing we have to do is put this in words. That means in context. So how do we say this in context? So what does P represent? P represents
Proportion of people that took which the vaccine was effective on?
Is less than 0.62, which means it's less effective. Okay, so we got to put that in words. So therefore, we have significant evidence or sufficient evidence or enough evidence to suggest that the true proportion what did I say? Of people for which the vaccine is effective is less than 0.62. In other words, it's less effective. Therefore, we have significant evidence to suggest that the true proportion of people for which the vaccine is effective is less than 0.62. And you're done. So what we ended up doing was we called them a liar. We said, no, your claim is wrong. 0.62, it's lower than that. How do I know? Because my p-value is smaller than my alpha. Okay? All right. So we'll stop there and then we have a couple more problems, examples. All right. We'll stop there for today, though.